Again, welcome to the lab. Today is, I don't know, I lost track of what many labs there are, but I think it's lab 4. Let me check on that quickly here. It says lab 1. Lab 1 of thermophysics, which is really lab 4 for you guys. So this is basically the lab for, let me share with you the screen, okay? Let me find first of all the page so that I don't, it's lab 4, okay. Share. I'm going to share with you this one quickly, and then we'll go to the lab instructions, okay? As typical, you've seen this time and again. This is probably now you're accustomed to how this thing works. So in other words, you all have the rubric in here. It tells you how this lab is graded. And it also tells you when it's due. And I'm hoping that you guys by now have been used to the system so that you know exactly how things are graded, what you need to do, and things like that. So if you have difficulty with this one, you please let me know. There is one thing in here that's probably I'm going to ask you to do anyway, and we'll go through it, okay? So let's go into share the screen now for the actual lab instructions. Here are the lab instructions. Are you guys looking at Introduction to Thermal Physics lab? And again, I can't see the chat. Oh, I can. Yes or no? You're supposed to be looking at the PDF file. Is there a delay in the Canvas? I mean, on Zoom now? Harris, are you looking at it or not? Okay. Well, I'm going to assume that there is no problem, or else if there is a problem, I'm talking to myself, which is not good. Okay. So again, this is part of the rubric where everybody's supposed to be answering this part. As a strategy, try not to do this one first until at least you have a clear idea of what the lab is all about so that you can actually tackle this one. Please do not leave off points that are important. I mean, in the lab, if we're going to be discussing something, don't ignore that in the objective so that it's really has to be reflective of what's being done in the lab, okay? So again, this is part of the stuff we saw in lecture today, the specific heat, the amount of heat. The symbol delta in here is actually a mistake. I should really have not used it, okay? And because I'm basically using the lab instruction from a long time, so I'm still using that symbol. It should really say Q. Doesn't mean change in heat. There is no such a thing. It's heat, like work. It's work. There is no change in work, okay? That's basically in a nutshell what it is, okay? In a differential form, yes, you can say an amount of heat added or removed during such and such process, maybe, okay? But overall process, it's an amount of heat that is either added or removed from the system. Obviously, if delta T is positive, then you added heat. You heat up an object so that its temperature rose. If delta T is negative, that means you removed heat from the system, in which case its temperature went down. So this is basically how this expression is. C for water is 1. As a matter of fact, there is a table in here with specific heats in here, and you have the air, aluminum, you have all of these materials in here, and here is water. Water is practically 1, okay? And the units for it is calories per gram per degree Celsius. If you want to convert this one to joules, a little calorie, one small calorie, is 4.19 joules, okay? A big calorie with a big C is actually 1,000 times that much, which is 4,190 joules per kilogram in that case per degree Celsius. Okay, so these numbers are all in grams per calories per grams per degree Celsius. So if you're going to find them in kilograms, you have to multiply each and every one of this by 1,000. Okay, so you have air, which has less specific heat than that of water, about a quarter of that, about 1,000 joules per kilogram of air. Okay, you have aluminum, which is slightly less, and so on and so forth. All of this material is in here. Water in ice form has less specific heat than that of ice than water. Okay, so in other words, if you have water that you want to raise its temperature was sitting at -10 degrees, and you would want to bring it up to, let's say, for example, +10 degrees. In going from -10 degrees to 0 degrees, you don't need as much heat to heat it up. As a matter of fact, you need half the amount of heat to raise that temperature from -10 degrees down to 0 degrees. But then you need heat to convert it from solid to liquid. Remember, you have to go through the fusion process first, okay? So once then it has become liquid, then you're going to raise its temperature, in which case you're going to need twice as much heat as you did when it was from -10, from -0 to 0, versus from 0 to 10. So that is basically something to keep in mind when you're doing problems like this one, okay? And it's high still. Water steam also is about half too. So water has a high specific heat compared to anything, and it's on all of its forms actually compared to anything else that you see in here. Right? Gold, for example, has a very, very low specific heat. You don't need a lot of heat to raise its temperature, okay? So this is basically some of the properties of materials. In addition to that, we have the power, the rate at which power is transmitted from one end to the other end of a material. So the length of the material in this case did I use the expression backward? I think I did. I think I did. Hold on. Maybe this expression is not quite correct. Is it? Yeah, it's not L over A, but it's A over L. So please fix this expression, okay? This is wrong. It should be A over L, not L over A. Come on, what is that damn thing? Oh man, can't write. A over L. Please correct this expression, okay? This is not correct. It's not. Obviously, the longer it is, the less heat transfers. So the thicker the wall, the less heat is transferred, not the other way around. Not the thicker the wall, the more heat you're going to transfer. That's why it's nonsense, okay? The other way around too is that the bigger the area, the bigger the window, the more heat you're going to escape. So if you make a small hole, for example, there is less heat that is going to escape there if you make a bigger area. So that's why this expression is backward, okay? K in this case is here. This is in calories per second, of course. This is an energy per second, that's watt. and then per centimeter. And how would you know that the answers are this one is wrong? Just by looking at the units for the units for K are 1 over distance, okay, not the other way around. To match this A squared, I mean distance squared over distance in here to fix the units correctly. And then per degree Celsius because you have in here. Again, from the lecture, guys, you have seen that delta T doesn't matter if you use Kelvin in this case, and in this case too, or you use centigrade Celsius, because of the fact that the difference between the two temperatures is the same. Since the centigrade is just a shifted value from the Kelvin, it's only basically you add 273 to whatever degree Celsius, and then you're going to get it in Kelvin. So in here, the temperature doesn't matter. So the fact that you have them per degree Celsius could have been per Kelvin, it's the same thing, okay? So these are the expressions that we saw in lecture. We saw it correct in lecture, so we had it correct in lecture. In here, in this lab instructions, this is, please correct it. It should be A over L, not the other way around. Make sense for you guys?
Yeah, it does.
Okay, please fix that, everybody in here, and the ones who are watching later on for the lab instruction, please pay attention to this detail. It might throw you off, okay? Especially when you come to exam time and you're confused now, is it A over L, L over A? Just think about it. A thicker wall will have, you will have very little heat leaving room than if you have a very tiny wall. Thin wall going to have very little effect when it comes to thermal insulation, okay? So look in your home. Okay, before we do that, this is again the conductivity. Air is usually an insulator, so it has a low conductivity. Aluminum is a metal, so it has a high conductivity. Carbon dioxide, which is really a poor conductor. Concrete, which is a little bit, it's still poor conductor. Otherwise, we have electricity coming from the walls, which is mainly concrete. Copper, which is a very good conductor of electricity. It's actually used in the wiring. It's a good conductor. Glass is an insulator. Gold is very good conductor. Iron, which is a good conductor. Lead, which is also conductor. Metal, all of the metals are good conductors. Nitrogen, which is the air basically, and that's why you see this number and that number is not different, because nitrogen is the main component of air. And then oxygen, which is the second most common component in the air. Both of them are insulators actually. They have very low conductivity. Soil, which is also a poor conductor of heat, so you can use it as an insulation. So animals that live under soil, for example, in the winter, they really don't see a lot of change in temperatures. That's why if you go under the mountains, for example, if you go to caves and things like that, you don't feel a lot of weather change, whether it's too hot outside or too cold inside, because of the fact that it's mainly an insulator. Water, which is insulator when it comes to heat, okay? This is water with no, water steam, I guess, and all of the water in general with no salts in it, okay? With no minerals in it to make it conductor of electricity, okay? And the same thing with wood, which is a poor conductor. Zinc, which is a metal, also is a conductor of heat. So just look at this one in here. All metals are good conductors of heat, basically. Okay, and that's their specific heats. The highest apparently is copper, which is a very, very good conductor in here. Okay, that's why if you happen to be sitting on in a wintry day, you're sitting, for example, on an aluminum bench versus a wood bench. What is the wood? Here. One of them has a very low conductivity, 0.5, the units, relatively speaking, with the one that is made out of aluminum, which is 1,000 times more conductive than the wood. Okay. So again, look in your home for a steel plate or a spoon, whatever it is made out of a metal. Okay. Iron, aluminum, doesn't matter. Okay. And a wooden plate or a spoon, something that is, for example, the stirring thing, if you can find a wooden spoon, okay? The one that you used to stir the soup in the kitchen. Leave both sitting in thermal contact with the countertop of the kitchen for quite some time. Basically take the two and put them on the kitchen, okay, table. to make sure nobody bothers them. Nobody takes this one and put it in the refrigerator or uses on soup or anything like that. Tell them I'm doing an experiment, okay? Are the two plates at the same temperature, or the two items on the same temperature? Think of the first zeroth law of thermodynamics. Both of them are in contact with the air. What do you guys think? After a long time, when you put them there, would they be in the same temperature, or one of them will be a different temperature than the other? Don't touch them yet. Zeroth law states that an object, basically, that's actually, an object, which is in this case the wooden spoon or the wooden plate, and leave it in contact with the air until it reaches thermal equilibrium. Now, the iron or the aluminum spoon or plate, you put it in contact with the air and let it stand, or the countertop, both of them are the same thing, and let it there for a long time until it reaches thermal equilibrium. The question is, do you think the two plates or the two spoons have the same temperature or not? What do you guys think in here?
I think they would. I think they would have the same temperature.
Well, by virtue of the zeroth law of thermodynamics, because both of them are in thermal equilibrium with the surrounding, which is both of them are in. Therefore, okay, make sense?
Yeah.
Okay, very good. So now simultaneously place one hand on one plate, on each plate, or one finger on each spoon if you're using spoon. So put your finger one on this one and one on the other one. Does one plate feel cooler than the other? If so, which one and why? Of course, you're going to do this, okay? I'm not going to tell you to do. I'm not going to tell you the answer because I don't have them first of all in front of me. So again, I want you guys to do this after you put them for a long time. So you have a wooden object and a similarly sized a metal object, aluminum or iron, doesn't matter which. Put them after you are sure the zeroth law did its trick in a sense that both of them have the same temperature. Put your finger on each or your hand on each. Or use both hands, of course. One hand on one and one hand on the other, or one finger on one and one finger on the other. And then, does anyone feel cooler than the other? And if it is, why in the world it is? Make sense?
Makes sense.
Okay, very good. So refer to this table for your answer, please, okay? So if you use the aluminum, you're going to refer to the aluminum properties. If you use iron, refer to iron. And if you happen to have gold plates, use gold. If you have to have, what else? I don't know. That's probably the common items that people. Silver. There is no silver in here. Okay. So don't use silver, okay, because you don't have any data for it. So this has several parts in it. So you have question one, and then you have another question and a third question. Don't forget the why. Okay, that's important. And the why is coming from this table, actually. Explanation from here. And using this formula, mainly, okay? This one has nothing to do with it. No, it does. No, this one has nothing to do with it. Okay. Now, place an ice cube. That's another thing. This is, I need you to send me a picture of this, okay? So I'm going to ask you guys to upload a picture of this part. So you're going to place an ice cube on each, not a video, a picture. Okay, video is going to be too long if you do it with a video. You're not going to have enough bandwidth to upload it. So what you're doing is take two ice cubes, hopefully of the same size. If you can crunch them, try to take similar amounts, okay? Similar quantities, okay? And then place each on a spoon. or plates. If you use the plates from before, doesn't matter whichever you use, you're going to take one and put it in here and one and put it in there. And then watch on which plate or which spoon does the ice cube melt faster? On the wooden plate or the wooden spoon or the aluminum plate or aluminum spoon? Of course, if you didn't use aluminum and used iron, you're going to sub the correct things for that, okay? How is that the metal plate feels cooler and melts the ice faster? Okay, if you use the metal, you will notice that actually the ice will melt faster on it, yet probably it feels cooler, okay? So you're going to explain what's going on. So in here, it's a detailed question, by the way. Those questions require an understanding of what's going on back to these points in here. Micah, since you just joined us, make sure you fix this thing in here, okay? But please also watch the, how long have we been in here? The 20 minutes recording, because we talked about these questions and hopefully catch up with them, okay? Okay, very good. So basically in here, so the second question is require some thought too, okay? Please don't just give me short answers that really don't express an understanding of what's going on in terms of heat transfer and what's going on in this case, okay? Definitely there is an object that is not sitting at the same temperature with everybody else. And that object is you actually. Yes, probably the spoon, and yes, probably the metal spoon or the wooden spoon or the countertop or the room temperature or the air, they all probably have the same temperature. But don't forget yourself, you have a higher temperature than them on a regular basis, okay? Unless it's scorching hot outside, in which case you're going to be cooler, okay? In which case you have other problems to worry about other than this experiment. So your temperature is higher, so in this case, so you have to watch for which way the heat is going, okay? So in this experiment, basically what you're doing, you're taking an ice cube in this case, which is probably not sitting at the same temperature as everybody else, two ice cubes, and you're putting them on two different objects with different specific heats and with different conductivities. And then you're watching one of them melts faster than the other. And you're probably going to watch the metal, the one sitting on the metal, melt faster, yet it feels cooler before you put in it. So why is it going faster on it then? Okay, so that's question 2. Question 3. Suppose you are going to defrost some hamburger meat for dinner tonight. Would you better be defrosting it wrapped, of course, by laying it on a wood cutting board or a metal dish? And explain. This is related to the previous questions. If you didn't do the first 2 questions correctly, you're going to have difficulty with this one, okay? So this question is related to the previous 2 questions. Okay. So all of this stuff is pre-activities to what you actually are doing. So this is a home. I need a picture of this thing, of your setting, okay? I don't need really. So after you put the ice on the 2 spoons, wait for it to melt a little and then take a picture and upload it with your lab report, okay? To show that you actually did the activity and you didn't rely on some preconceived ideas or you Googled it or something, because after all, we're supposed to do and not watch. Okay, again, here is the definition of the temperature. The formal definition of temperature is change in internal energy per unit entropy at a constant volume, or the change in enthalpy per unit volume at constant pressure. The problem is that this definition is meaningless to introductory physics. A more meaningful definition would be the temperature is the average internal energy of atom or molecule per unit volume, consideration included but not limited to the entropy, enthalpy, and all of the other things, okay? Now, heat, this is any transfer of internal energy from one body to another due to a difference in temperature, okay? So so this is basically the key, the things in here. Internal energy, this is the total energy of a sample. This includes kinetic energy due to motion, translation, vibration of the amount of molecules, and so on and so forth, okay? So question 4. After you read this stuff in here, and hopefully you understand it, if you have a question, please let me know. please define the following in terms: internal energy, heat, and temperature. I don't want you to copy and paste. Please put it in your own terms showing understanding, okay? Your own words showing an understanding. Okay, which is hotter? A red hot nail or a bathtub filled with ice water? The key word in here is red. For a nail to be red, it really has to reach much higher temperatures than 100 degrees Celsius. And the water is already ice water, meaning that its temperature is hovering around 0 degrees Celsius. So one of these two is hotter. It's obvious in this case which one is it. So which one do you think is hotter?
Did you want us to say?
Yes.
The hotter one would be the red hot nail.
That's absolutely right. You nailed it. Very good. So what has more internal energy then? That is a tricky question. Although this one is hotter, this one is ice water, but it's a bathtub full of it. So the internal energy now is really per molecule. So you ask yourself, how much matter you have in one versus the other. So hopefully that will clarify that the water should have more, and because you have more of it in this case, albeit it's a lower temperature. So saying that you have a higher temperature doesn't mean that you have more energy. It depends on how much matter you have, basically. That is the key there. If the red hot nail were placed in the bathtub with ice water, does the ice water absorb more, less, or the same amount of heat by the red hot nail? So in this case, it's obvious, okay? So it's going to exactly take whatever the other one offers it, okay? This is the basis of calorimetry that we did earlier in the class today, okay? Measurements, so this is the calorimetry now. This is basically the definition of it and all of the processes. So for water, we're going to take it to be 1 calorie per degree Celsius per gram, okay? So again, the definition is for it to raise the calorie is on the specific case to raise that of 1 gram of water that have 1 calorie of heat to change its temperature by 1 degree Celsius. Actually, the formal definition is not just any 1 degree Celsius. It's between 14.5 and 15.5 degrees Celsius, okay? And if you look at your book, that is exactly how the definition is. So it has to be doing that. So that's how the calorie was defined. And it is a lowercase c, not the uppercase c. So this is the way C is spelled in here. Okay. So again, this is how you measure this, the specific heat. So if you have, for example, a solid in this case, again, please ignore this delta. I think I'm going to remove it in the next incarnation of this lab, okay? I'm going to convert it back to its original form and then remove that delta because it doesn't mean much, okay, in this case. So for a solid, in this case, you went from so the temperature that it reached is the mass of the water is MW and its mass is so the W in here doesn't stand for water, is the warm basically. So it was hot, now it dropped its temperature. So how much heat it lost in this case? It lost TH minus TW, this is the change in temperature, times the amount of solid in this case times the specific heat. Likewise, the amount of heat that the water would have gained, don't forget that this is one except that if it's in calories, but if it's in joules, it's going to be 4,190 joules per kilogram per degree Celsius, okay? So you have to be specific in here in terms of this value for water. It's not always, it was definition based on the calorie, and Mr. Joule found the correspondence between what a calorie is and what a joule is. Of course, he didn't call it a joule. It would have been really not proper to invent something and call it after yourself. People later on called it after him, okay? After they saw what he did in this area. Anyway, so equilibrium in this case dictates that the two heats are the same. So if I can measure this temperature, the temperature of equilibrium, if I know how much the element in here was started with, if I know how much the liquid had temperature, So in the middle temperature is somewhere in there, depending, of course, on the specific heat. So if this is TH, and this is TC, in the case of water, what we notice is that the equilibrium temperature will be very close from it because it has a higher specific heat. In order to drop this temperature in here, you're going to lose this much heat, and this much heat will barely raise the temperature of the water because it has a high specific heat compared to a lot of elements. So this is the same amount of heat, yet the drop in temperature is high enough in this case to account for the small specific heat of this solid versus that of the water, okay? Anyway, this is a way for me to measure the specific heat of any element if I know one. Since I defined this one for water, then any material can be used. We can find the specific heat of anything we want. And this is what we're going to be doing in this lab, basically, okay? In this lab, this is the expression that we're going to be using. So what we have, the mass of the water, we have the mass of the solid, which we can vary, the temperature, the TC is going to be fixed for you guys, so we're not going to be playing with it. TH, you can change it. TW, you're going to measure it. From here, you're going to find what the specific heat is. For that, you're going to come to this link. So I'm going to click on this link. Oh, man. And let me stop sharing that screen and share with you this screen. So this is where you are. Do you guys see this one in here? Yes or no?
Yeah, I see it.
Yeah, I see it.
Yeah, calorimetry. Let me remove it in here and put it in here. So we have the experiments in here, if I can. We're going to run the experiment in here, okay? So choose the liquid. So we're going to be using water for all of this experiment. The temperature, you cannot change it, okay? If you want to see the specific heat, it's actually 4,184 joules per kilogram. So you don't need to see this one. You can use the ones that is given to you in calories. That's the same thing. So the amount of water now depends, okay, on the instructions on how much to put. Okay, so if I put, let's say, for example, I put 100 grams of water, 100 grams. Let's put 150. Okay. And solids, we're going to choose, let's say, for example, I don't know what the table is asking to do to start with. So we're going to start with aluminum, okay?
Wait, Professor, we're viewing a page.
Okay, hold on, hold on. You're not looking at this one?
We can do it now.
There.
Okay, I lost it myself. Which page were you looking at? Okay, so the liquid now first, okay? Let me go back into the liquid. You're with me now?
Yes.
Yeah, I'm
Let's see,
following along.
the water.
At 150 grams of water, okay? So the temperature, let's make it 20 degrees Celsius, okay? For this purpose. And let's choose a solid. And here, aluminum is the first one, okay? No, why is this not doing it? So let's go back to water. Why? Okay, 150. Okay, so once you choose the temperature, you have to click next. You have to have both of them selected and then go next, okay? You don't do next, you're still in stage 1. So now we're in stage 2. So now we're going to choose, oh man, that's bad thing in here. I forgot. Okay, let me reset this thing in here. Okay, sorry about that. Let's run the experiment. Okay. So it's in here that we have to choose Yeah, I'm sorry, I had it correct. Okay, I'm sorry about the. So we're going to choose water. We're going to choose 150 grams. We're going to choose a temperature of 20 degrees. And next, we're going to choose a solid now. And why is it not giving me any solid in here? Is it because it's expecting it in the opposite? Okay, so we're choosing the solid now, aluminum. Let's take a maximum amount. Temperature 160 grams. Next. Oh no, this is the only way this experiment is going to run. So the temperature is fixed for you, 20 degrees Celsius. So we're going to choose the amount of water that we have, 200 grams. Oh, this is the container. Because, I'm sorry, my brain is not here yet, okay? So I'm sorry about that. So basically, you take a solid in this case, and you're going to put it in here, okay? You're going to watch the reading of the temperature in here. The temperature is 20 degrees Celsius, I'm sorry. You watch the reading, and once you're ready, so right now we took 200 grams of water sitting at 20 degrees Celsius. This substance is at 160 degrees Celsius, and it's aluminum, okay? And we took 50 grams of it. We took the maximum in this case, sitting at 160 degrees. Now, if we mix them, the temperature should be roughly around 20 degrees. It's going to increase the water temperature, and this one will decrease its temperature, of course, until we reach the thermal equilibrium, okay? So if we go next now, one of the options that we can show the graph in here, okay? If we show the graph, we have aluminum, we have water in this case, and we have their temperatures, okay? So water's temperature starts at 20 degrees Celsius. The solid in this case, namely aluminum, has a temperature of 160 degrees Celsius. So the temperature should be a little higher than 20 degrees Celsius when they reach their thermal equilibrium. So let's start this, okay? So we took the substance basically and put it in there, and you closed on it, and the temperature now is increasing of that of the mixture. The one that is coming from the aluminum is dropping very fast until this stabilizes. So you're not going to report the data until this somehow stabilizes, in which case you have reached the thermal equilibrium. So at this point, we don't have thermal equilibrium yet. But now it's basically stabilized at 27.17 degrees. So the temperature of the water rose, and the temperature of the aluminum dropped, but dropped from 160 degrees, not from, not very close from it, but it came close to thermal equilibrium with the other one. So let's reset this experiment and choose a different solid in here. Solid. And let's say, for example, iron, okay? And let's take again, same thing, 50 grams, and let's say around 160 degrees, just to see the difference. This liquid, we're going to still take water, and we're taking 200 still at 20 degrees. So in this case, I expect a temperature, because they have different, they were going to reach thermal equilibrium, but they're going to reach a different thermal equilibrium because specific heats are different now. Actually, it's coming a lot faster now than before. So the temperature should be not 27 degrees, but it should be something closer to 20 degrees. You have to agitate a little bit in here to help it basically with the heat exchanger even. So the temperature came down to 23.66 degrees, okay? So again, let me stop sharing the screen and go back to my PDF file, if I can find it. Where is it? There. Okay, so what you're supposed to go is follow these instructions, please, okay? When you visit the link, choose experiment tab. From the tab, choose solid. So I was not following the instructions in here. Solid, and select first aluminum from the drop-down menu. From the mass slider, choose a mass in grams, record the mass of the solid in the table below. So you're going to come in here and see what you have used, okay? So that's the mass that you have used. You don't have to use the mass that I have used, okay? Please choose different numbers. From the temperature slider, choose temperature high enough in degrees Celsius. Record the temperature again. You don't have to choose a temperature that I have used, okay? Probably could be a higher temperature for the solid. So again, that is another one. Then you don't need to check the specific heat because you're going to be measuring it anyway. In the left pane, the button choose next, so we had to choose next, becomes available. Click on it. The right selection becomes highlighted, and there choose a liquid, choose water. So we're going to choose water. From the slider for mass, choose a large enough mass in grams. You don't have, again, to choose 200. You can choose whatever. Please don't choose 200, okay? Choose a number, and that makes it a little bit more, calculation more, at least believable in the sense that it is not rounded numbers, okay? Again, we're going to have the mass of the water in here in grams. Note the temperature is fixed at 20 degrees, so we're going to put in here 20 degrees, okay? Okay, so then run the experiment, click on Start and Simulations, and record the equilibrium temperature in the table below. What is the temperature in here? Okay. Oh man, you're going to have the temperature of equilibrium. To calculate this value, because you're going to come into this expression now, after you find TW or T equilibrium. So you have the specific heat in here, because the specific heat of water is going to be 1, okay? You have the mass of the water in this formula, whichever mass that you ended up from this one in here, okay? Divide by the mass of the solid in here, times the difference in temperature, the equilibrium temperature. Remember 27 degrees, the first one, minus 20 degrees Celsius. You might find a different value than 27 if you choose different masses, okay? So don't rely on the numbers that I have done. You have to come up with your own numbers in here. So it could be more or less depending on how much heat you started with, and how much TH you start with, and how much mass of solid you have, and how much mass of water you have. So it's going to be a temperature. For my case, I'm going to put 27, for example, for aluminum, divided by TH. I think I use 160, and minus, in this case, 27 point something, okay? And I'm going to report the value now of the specific heat here, okay? And that I'm going to compare it to this value and put the percentage error in here, okay? So that is basically how we're going to do it. This is a known value. You're going to take the difference between this and divide by that one, and you're going to have a very small or big error in here. In this case, this is strictly positive. So regardless, if you end up with this number being more or less, just take the absolute value, okay? Again, you put the same stuff for copper, iron, silver, and tin, okay? So, and the values are given. Here is the value for silver because it's not in the table up there, okay? Given that water has a relatively high specific heat, why will using too much water give you poor results? Let's say, for example, you came in here and used the maximum amount of water in the experiment. This is not good because of the fact that the specific heat of water is very, very high. You need really a huge temperature for the metal to see significant change in temperature. Because if you brought the metal, for example, let's say, for example, in 30 degrees Celsius, you're going to have a problem. Okay, let me go back to the experiment in here. Let me stop sharing. And let's go back into the same screen. Let's reset. Let's choose iron, for example. I'm going to choose, for example,
30 grams.
30? Okay, 28 is good. I'm going to choose a temperature, for example, of the increments of this number. So next, I'm going to choose water. I'm going to choose a lot of things. And next, I'm going to show the graph. You don't need to do the show the graph. It's actually for your own visualization. That's all, okay? Let's start this now. We're going to put that much iron into this much water, close on it. Look how much temperature change is. Okay. So if you use a lot of water where the material was not too hot, and this one is hot actually, 30 degrees is hot, okay? You're going to see hardly any change in the temperature of the water. That's when we do this experiment in the lab, we really use as much as needed from the water only to cover the piece of matter. So basically you take an object that you heat it up and you put it in water. You don't want a lot of water, otherwise you're going to wait forever to see the increase in temperature, and probably your probe is not going to pick up any change in temperature. So that's the question basically of what he's asking, okay? Why do you have to use not too much water? Is because it has so much high specific heat. So it's going to absorb all the, especially if you don't start with a lot of mass from the solid, or it's barely hotter than that one. So the change in temperature will be so small that probably you're not going to pick it. Remember, it started with 20 degrees Celsius. Now it barely went 0.15 degrees Celsius. Probably if you're using thermometer, a regular thermometer, you're going to say, hey, did not change the temperature, okay? Especially if you add the air, which is in contact with the water and in contact with the substance. By the time you move it in there, probably it's dropped so much that it's practically unreadable. You're going to get zero data. Make sense, the question? Yes?
Yeah, makes sense.
Okay. So this is the question that basically is in this part. Question. When comparing the heat capacity of most materials such as rock and sand to that of water, how does it account for the mild climates near oceans and lakes and the extreme hot and cold climates found in the deserts? I ask you guys to Google this one if you like. Basically, this is the point in a nutshell. For people who live near the ocean, okay, if you are near the ocean, what happened? During daytime, there is a lot of heat coming from the sun. The sun heats basically both the ocean and the land. Because the ocean has a very high specific heat, its temperature rises, but very little. Compared to the sand, the oil, the ground, which you can see from the, what is this in here? From the specific heat, have a very low specific heat, so its temperature rises higher than that of the ocean. So in this case, this will be warmer, this will be cooler. So the hot air now basically moves around, cools above the ocean, comes from the ocean, rises temperature because it's a higher temperature and closes the cycle. So you feel a breeze coming from the ocean. The ocean now has, because of its high specific heat, will force the air to move this way. At night, it's the opposite. At night, because there is no sun, so there is no reason now for it. So the drop in temperature overall basically causes the ground to lose a lot of its heat and its temperature drops below the ocean. The same thing, the same amount of heat is also lost in the ocean, but the ocean has a very high specific heat, so the change in temperature stays the same. So in this case, the ocean will become warmer than the beach, in which case now heat is flowing in the opposite direction. So oceans act as a normal regulators of temperature, whereas in the deserts, there is nothing that plays that role. Come midday during summer, it's super hot, scorching hot, because of the fact that the heat is absorbed by a lot of it is absorbed and the temperature rising for that. And in the winter, it's the opposite. If you ever lived in the Midwest, you know exactly what I'm talking about. The Midwest is hotter than California in the summer and super cold, freezing cold basically in the winter, more than people who live in the oceans and near the oceans basically in general. So this is the question basically related to weather. Again, it has to do with convection. It has to do with specific heat, okay? And I recommend that you guys Google this or look it up in the book. I think there are some details and instructions in there. This is the conclusion for your lab. Again, please go through the activities, understand what we're doing in here, fix the mistake that is in the formula for the heat, the current, or what is this? What do you call it? The current of heat. Okay, fix that. The power at which heat is dissipated by conduction. fix that one, so to help you basically explain some of the questions that are related in this lab. Any questions? Okay. If you guys don't have any questions, I'm going to stop the recording. If you want to work on it now, that's fine. If not, that's fine too. I will see you guys on Wednesday when we do finish this chapter. I'm going to stop recording now.